All right, folks. Well, welcome. My name is Chris Ruger, and I'm here to give a Doug talk, which is a data user group. I'm associated with DF Hines, and we give regular talks on various big data technologies. And tonight, I'm going to talk about Flink. Flink, especially within the context of how Flink might be used as an alternative to Spark. Especially with respect to the streaming capabilities. But what I want to do is make sure, make you aware of Flink, because it's not nearly as well known as Spark, but I believe it has much the same capabilities, if not exceeds Spark's capabilities in some areas. So let's get on with it, and let me show you what I want to talk about. Breaking it down into basically 6 major sections here. First, I want to give you an overview, and then we'll go into the components and the programming model of Flink. And we'll do some discussion on batch processing. And I'm going to spend probably the bulk of this talk on the streaming, because I think the streaming is very interesting, and I think apropos for the way technologies and IoT and whatnot are evolving nowadays. And I think it's very fitting that we talk about streaming. Then I'm going to talk about the SQL capabilities. Since SQL is going to be a big interest of data scientists and other folks of that nature. And then finally, we'll talk about the fault tolerance. And at the end, we can, if you have questions, I'd be glad to take those, and we can also get you the slides and my contact information if you have questions beyond this talk. I'd be glad to help you out. So let me start off by just giving you, start out at the 50,000-foot view and talk about a little bit about what Flink is. It's a lot like Spark. It's an open source framework for distributed stream processing that is highly parallel, and it works on massive amounts of data, terabytes, petabytes, largely in parallel with large clusters of data that will process tremendous amounts of information for you and do various transformations in a very, very efficient manner. So these are some of the highlights of Flink. It's designed to provide very accurate results, especially with respect to streaming and handling out-of-order data. It's stateful and fault tolerant, which means that if you're running your Flink application and it happens to crash or go down for whatever reason, or if you even want to take it offline and do maintenance and bring it back up again, it's easy to do that. Again, as I mentioned, it runs at very large scale. We'll see a little more concrete examples of what I'm talking about with that. Where did it start? Flink's been around for quite a while. People don't know this. It's been around since 2008. It started out as a research project in Berlin at the Technische Universität. I'm not going to pronounce this correctly, but the Stratosphere project at the Technische University in Berlin, Germany. The word Flink is actually German. It means agile or swift. That's hence their logo. A swift darting squirrel in your backyard, I suppose. And it became a top-level Apache project in December 2014. And here's a critical thing I think you should know about Flink. The streaming was built in from the very beginning, at the very lowest level. So it wasn't an add-on. It was something that they started with. And I think it's made Flink very mature in that regard. Here's a quick look at who's using Flink. You got some big names that are involved. Some of the better-known names here are Capital One. In fact, I'm going to reference one of the folks from Capital One in a minute here. He's done a lot of research on Flink, especially with respect to how it compares to Spark. Alibaba uses it. Uber's using it. Uber's using some of the streaming capabilities because you've got to match up drivers and cars and passengers in real time. And this is where it excels. Now, why are they using it? I want to mention Slim Baltaji. He's one of the better-known folks, advocates of Flink out there. And he's done quite a bit. If you Google him, you'll find a lot of his talks and his slides and presentations. And he's called Flink the 4th generation of streaming. That's the key point I want to make here. He considers just plain old vanilla batch processing or MapReduce is the 1st generation, and then he considers Spark the third generation. We'll see why he thinks that. And then the Flink is more the fourth generation. It's got the latest streaming capabilities. So these are some big names that are using this, and I would invite you to take a look at some of his talks. He goes into much more detail on the comparisons between Spark and Flink. Again, it's a in my view, and in the view of many other people, it's a very good alternative to Spark. Here are some of the highlights that make it sort of appealing as a solution for you. It's got low latency streaming, and it uses the true streaming. It doesn't use micro batches like Spark. It has what they call native closed loop iteration operations for graphing, machine learning processing. What does that mean? It means that you never have to jump out of your Flink program into a loop and then go back into it. It's going to handle that all by itself. If you have Spark or other engines, you'd be doing this in a loop, and so you'd have to write code. So the more code that you write, the more chances for complexity and errors and bugs and whatnot, things of that nature. So Flink tries to avoid that, and it has what they call the native, closed loop cyclical kind of operations for you. It has a custom memory manager. Remember, one of the things that makes Spark and Flink much more efficient than traditional Hadoop MapReduce is they do everything in memory. Hadoop writes some of its temporary results out to the file system. So these engines are both much faster than traditional Hadoop MapReduce. And again, as I mentioned, since it's trying to do a lot of this for you, there's less code and maintenance for you to be concerned with. And here's another comparison I found online, and these are I've looked at quite a few of these, and they all seem to have the same sort of theme. And the theme is that they're both great products. They both do a great job. The fellow here is a product manager at MapR, and I'll give you a link there to his talk. But the bottom line from what he says is that if you're looking for error detection in real time, they're both good. But if you need, if you're looking for a solution that has not only detection but a way to respond to an error very quickly, he actually gave the edge to Flink on that regard. Because, again, it doesn't have the micro batches, which I'm going to show you a pretty graphic example of what that involves, which is right here. So when Spark was written, it was written more as a batch programming. Now they're catching up very rapidly with respect to the streaming, but the limitation that they had was that since they didn't have the true streaming capability built in from the start, they had to use what's called micro batches, which is simulating a stream by making very small partitions of the data as it comes in. But it has to stop and sort of gather some data together and then present it to you as though it were a stream. And the analogy that I have here is kind of like if you consider your water hose a stream of data, then it would be almost like filling up a bucket and then when that bucket's filled, then pouring it out into whoever wants to process the bucket. And so there's overhead involved in doing that. That's what a micro batch, you can think of that as a micro batch for to compare it for Spark here. But Flink, you don't do that. You don't have to empty a bucket. It just keeps coming. So when they talk about micro batches, keep this in mind as a very good metaphor. I think it'll help you understand it when people talk about these comparisons. Now, what I wanted to show you is the next slide here, the runtime environment. It's very similar to Spark. A lot of these frameworks that all operate the same way. And in this case, you basically have three main players. You have your application, which is your Flink program, which is Java code typically, and it's jarred up as a jar file. And then you would submit that to something called the job manager, which is sort of coordinating everything. It's coordinating how your program gets run. Because remember, your program is going to get run not on one machine or two machines, but hundreds of machines, thousands of machines, all in parallel all processing your data simultaneously to give you incredible performance, parallel performance. Those nodes are called task. They're basically called worker nodes. In Spark, they're called the cluster manager and worker nodes, I believe. In Flink, it's the job manager, and there are task managers, which are handling, each task manager is handling a chunk of your data as it's being processed. And so when you have, the more machines you have, obviously, the more parallelism you can have. But these are the major players. So again, we're coming in from the 50,000-foot view, just to give you an idea how this all fits together. This is what it would look like when you set up a Flink cluster. How do you actually deploy your application? So I wanted to give you a very concrete example. First of all, the clusters can take various forms. There's something called a mini cluster, which I use on testing Flink programs, which if basically you can write a Java main right there in Eclipse, which I use. You can right-click and say Start. Run as Java application. This is just for unit testing, of course. But it'll start what's called a mini cluster right there, and it will run your Flink program. It doesn't work for every single case, but it works for a lot, especially if you're just debugging to make sure that your data transformations and your operations are being performed properly. Then it has what's called a standalone cluster, which is you run a Flink job manager and task manager. It's its own cluster. You can also run it inside of Yarn. It's part of a Hadoop cluster, and you can run it in a Mesos cluster as well. What do you do to actually deploy your app? As I mentioned, you would take your application, you create what's called an Uber jar or a fat jar. And what is that? That is just your program, your classes, plus the transitive closure and dependencies of anything that your classes depend on. So it goes, you can do this very, very easily with Gradle. You can do this with Maven. You just basically have a task in your build that says, give me my jar file. And then you would take that jar file and you would submit it to the Flink job manager, and it would take care, it would run all the magic and run it for you. So that's the overview. Let's talk about next some of the high-level components and the programming model that Flink uses. All right, so what I want to show here, this is right out of the documentation. And this, again, I believe in always starting out at the 50,000-foot view and kind of zooming in on things. So we're going to start at the very beginning here. This gives you an idea of all the various pieces that make up Flink and the different layers involved. So at the very bottom, as you might imagine, you've got software that's involved with how to run your program in the various kind of clusters that we've talked about. You can have a local cluster, you can have a standalone or Yarn, or you could even run it in the cloud, as it's indicated here. The next level up is, surprise, the streaming layer. So this is built as your next layer. It's the foundation for all of the APIs above it. And you can see in the next slide that we have two main APIs. One is for batch data, which is called a data set, and the other one is for the streaming, which is called the data stream API. Now they're very similar. In fact, you can think of since everything in Flink is really the conceptual model that they try to build the framework into the framework from the very beginning, is that everything's a stream, and that data sets and files and things of that nature are simply just a stream that ends. It's a bounded stream. You can think of it that way. So they tried to build that. I think they might actually be merging those two APIs in the future. I think I read somewhere on the documentation that will become one API. Right now they're two. They're very similar. Setting up a Flink program is almost identical whether you're using batch or streaming. We'll see an example of that. Then on top of all that, now you've got the higher level APIs. And it's got, again, it almost matches component for component what Spark does. You've got a component that handles the complex event processing. What's that for? That's for pattern matching. That's for finding trends in your data. Spark, again, has something very similar. You have graph processing. Again, something similar to Spark. You have a machine learning library built on top. We have then also the SQL API, which can take two forms. You can write using like a language, like Java or Scala APIs, so you can use direct language APIs to specify the SQL and the tables and what kind of queries you want to run and the search criteria that you want to use. Or you can basically write direct SQL. Again, I'll show you an example of that too. I want to start out high levels, and then we'll start drilling down. You can see some of the more details, lower level details of how you actually put a Flink. What does a Flink program actually look like? Here, I want to again right out of the documentation again. I just want to give you an idea here of the abstraction level, so that when you're building your application, this is something you can keep in mind. You can think about, where am I? What level of abstraction am I dealing with? So Flink, breaks these out for you very nicely, and it's right here in front of you, so you can tell what level that you. Sometimes you need to be at the data stream, data set API level. Sometimes you're up at the SQL level, but you can write programs at either of those layers. Okay, let's talk about Flink batch processing. As I mentioned, everything's a stream to Flink, really, and a file is nothing more than a bounded data stream. So you can think of a text file, you can think of a comma-separated value file. It's just a stream that ends, essentially. And we can do, just like Spark, we can do our transformations and we can do our operations. Transformations just change the data from one form to another. They're immutable. It doesn't really change the data. It creates a new set of data from existing data, but it's sort of more of a mapping procedure. Whereas an operation is something that actually computes something over groups of elements in your data set. The results are written to sinks, and here are some examples, very, very simple examples of what you might want to use as your sources and your sinks. So you can read text files, you can read comma-separated value files, Hadoop, obviously Hadoop distributed file system, S3, and every Flink program, if you look at the bottom, basically they all have the same structure. Data comes in, that's your source. You do something to it, you create some kind of computation, you get those results, and then you write them someplace. That's called your sink. Okay? Writing a Flink program is pretty simple, actually. There's only 5 steps, and here they are. You're just going to get an execution environment. You have to initialize Flink somehow, so it has a call for that, a couple of calls to set it up. You're going to say, here's where my data source is. Then you're going to specify, here are the transformations and operations I want to do on this data. You're going to write your results to the sink, and you're going to trigger the execution. That's the very last step, and that's because, like Spark, they both do what's called lazy evaluation. So you can write all these steps, and this will probably happen to you when you write your first program. You'll probably leave off step 5, and you'll say nothing happened. That's because Flink needs to see all of the steps of your program. It needs to know all the transformations and operations that you want to perform, because it's building a plan to execute those operations. And so it needs to know when you say, okay, that's it, I'm done. I want you to, please build my execution plan for me. So if you leave off step 5, you'll have a beautiful program that does nothing. And then if you put that in there, you'll get your results. So let's go down, drill down. I just wanted to give you a very brief tour into some concrete real code here. Just to give you an idea of what a Flink program looks like. So again, you should have these slides, and then you can study this at your leisure. But I wanted to at least give you an idea, so it's not so abstract. If we get into some concrete details of what a Flink program actually looks like. So this is what you could consider the hello world program of the big data world. It's called word count. And here's what you do. If you look on the right-hand side there, you would have something like an input file that consists of just lines of text. And in this case, it may be a delimiter, something that identifies words or different items. And what I did is I put red, green, and blue, and I'm just using colors, and on my second line I've got, and I think I got some typos over the commas, but you can disregard those for this discussion. In the second line I've got blue, yellow, and red. And what do we want to do? We want to find out how many times each word appears in the file. So what we expect as our output, we would say we saw the word red 2 times, we saw the word green 1 time, we saw blue twice, and we saw yellow 1 time. That's your input. Now this is just obviously a contrived example. You can imagine that in the real world you'd have a file that's petabytes large, and you wouldn't be doing something as trivial as this. But it does help to introduce you to some of the concepts that you're going to deal with no matter what the complexity of your program. You've got something coming in, you want to do a computation on that data, and you want to output the results. That's really the structure of any Flink program. And this is, again, this is about as simple as you can make it. So if you think about it for a while, you can see what we're going to have to do here. We're going to have to somehow identify the different words, and we're going to have to keep account. For each time we see a word, we want to say, I've seen that word 1 time, and then you want to add up all the words that are the same. So if and you can think of those words as almost keys. One of the most important concepts in this kind of data processing is most of the time your data has some kind of key value associated with it, although it's not. You can think of it as a key after the fact. It's not baked into your data. No one comes to you and says, here's the key for my data. You're just given a file. Your job is going to have to be, okay, how do I partition my data? Those are what the keys are. How do I separate into various chunks that go together? In this case, the key would be the word itself. Those are the things that are unique. So let's take a look at what you do here. I've tried to break it down into the 5 steps and very, very clearly identify them for you. In step 1, we just get our execution environment. Number 2, we get our data. I just go out to a text file here. It could be on your file system if you're running it out of Eclipse, just a local file. Obviously, you never do that in production unless you have maybe NFS, so that all the nodes in your cluster, the task managers can see your data. But you're going to get a file of some sort, either from HDFS or some other place. Then we're going to do our transformations and operations. Step 3 is where the magic happens. And I'm not going to go into really bloody detail of what this is doing, except to say at a very high level what it does is it takes each line and it breaks up the lines into individual words and it assigns the number 1 to each word, saying I've seen that word 1 time. That's sort of what this flat map is doing in the line splitter. And then secondly, we're going to group by words, and it uses something called a tuple. Flink has these built-in data structures that are very convenient that lets you combine, put together heterogeneous pieces of information that belong together. So in this case, what we're doing is we're saying we're going to have a tuple that has the word and the number 1, saying that we've seen it 1 time. And then we're going to group those. The group by 0 magic is the thing that says take all the words that are the same, put them together, and then do what with them? That's the next line. Sum them, add them. And that 1 there is not the one that I'm talking about with how many times I've seen it. The 1 refers to the 0, and the 1 here in this code here just refer to the index values of the tuple values that you're using. So we have a tuple of string integer. The string has index number 0. The integer has index number 1. You can also actually use F1 or F0 and F1. There's various ways you can reference these fields, but that's how you tell Flink how you want it to take the data that you're processing and do operations on it, how you want to group it, and then how you want to sum it. So let's say, we've got this, and we've got this data set called counts. What do we want to do with it? We want to output it someplace. We want to write it to our sink. That's what our next line is. So we're just going to, again, very simple, we're just going to write it out to a text file. And the last step, as I mentioned, we have to tell it that we want to execute the program. We want to give it a name. The name is going to show up on the admin console. Flink does have an admin console you can run, that administration console that you can use to view your running jobs. And so when you're running that and they're looking at what jobs are running on my cluster, you would see word count showing up next to this program. The final step here, I just want to show the line splitter, is basically it's a function that you write as you might imagine, because you have to tell Flink, well, how do I break up these individual lines? So you have to implement an interface, and there's various functions that it gives you for transformations. One of them is called the flat map. That's the one that takes basically a line. It takes one thing and it maps it to many things. So in this case, we map one line to many words with the number 1 associated with it. And that's so what I'm doing here with the line splitter. I'm just implementing that flat map function, and all I'm doing inside of that is I'm taking the line and I'm splitting it. I'm looking for some white space, which the / says. I'm saying I'm looking for a space basically, and that's how I identify the different words that are in each line, and then you collect them out, you put them in a collection, and you send them back to whoever's calling you, which is the up here at the previous line where we're calling flat map. That's going to, then have all of those entries that we talked about with the word count, with the word and number 1 associated with them. So that's about as simple of a Flink program as you can have, but I wanted you to see it because I don't want to have this be too vague or mysterious. I want you to see real Flink code, just to give you a feel for what what it looked like when you write one. So let's talk about the streaming. This is, I think this is where Flink is very different from from Spark, and where it really shines, I would say. It really, I think they've done an outstanding job implementing the streaming capabilities. So let's talk about, for a second here, what a stream, what is a stream? A stream is just, in my view, it's just an endless sequence of data. You could think of a Twitter feed. You could think of Internet of Things, where you have sensors monitoring a network, say, and they're sending data back to your data center, constantly saying, here's my health or telemetry data, here's how I'm doing, or I'm in trouble, I need somebody to come out and maintain me. And so you have this, this never-ending sequence of data that comes in. You can also have Kafka. A lot of people use that. You could use logs from your applications that are being put into a Kafka topic, perhaps, and maybe you want to read from that to see what's going on in what pages are people clicking on, what errors are happening in your application clusters if you have a cloud. And then you can also read from sockets. Maybe something's just coming in over the network. I use that quite a bit, actually, when unit testing a Flink program, just to simulate some data coming in over the wire that is a stream. So I want to also emphasize to you, when you start doing streaming, you have to really, you're going to have to do sort of a mind shift. You're going to have to change, take some time to change the way you think about time in particular. And you also need to think about how are you going to, if you have an endless amount of data, then how do you process any of it? Because if it's never ending, what do you do? And the answer is you break it up into smaller chunks that you can now do computations on. Those are called windows. So you might say, I want to look at all the events that came in from between time t0 and time tn, and I want to do something with them. I want to count, I want to compute a sum, I want to do some, compute an average, I want to identify a trend or something. And then the third thing you got to think about, which is a big deal, I think, is what happens, and this may or may not be important to your IT department or not, or your business's mission. What do you do about things that don't arrive on time? Because there's always going to be, if things are coming in from the outside world over a network, there's a possibility that there might be delays in how your data gets to you. Certain events have to occur in a particular order for your processing to be correct. And they might not arrive in order. They might arrive out of order. So you have to give a great deal of thought to that as well when you're designing your application. And you have to ask, you're going to have to ask yourself all the time, what is the acceptance criteria for my applications, for them to be both correct and fast, which is mostly what we're shooting for here. We want them to be correct, obviously, and we want them to have low latency and be very quick. And sometimes you need both. Sometimes they don't. Sometimes they matter a lot. Sometimes they may not matter a lot. But the nice thing, the good news, is that Flink has put in various tools and APIs to deal with these. So you have a lot of flexibility in dealing with this kind of thing. I said you had to think about how you change, sort of reprogram yourself in terms of how you think about time. And I want to emphasize this again here. This is critical in understanding stream programming. The most important observation that I think you need to make, and which, once I had this idea presented to me, then it made much more sense in writing a Flink program that do streaming. You have to think about when does something actually happen, which is what we have here on the left. We have an event producer. We have some kind of device or something. Something originates an event. So it starts, there's always a genesis. Something starts from, everything starts from something. And when that happens, you could think of that as truth or the gold standard, the source of truth in your system. That's when something actually happened. But that doesn't mean that's when Flink is going to see it, or that Flink's going to see it that way. Because in between that event, and your Flink program, there's wires and networks, and all sorts of things can happen between the time something happened at your source and then the time that you process it. So the time that it happened at the source has a special name. That's called event time. And that is the device itself, timestamps its data. And in Flink, a timestamp is just a long. It's just a Java long. It's the number of milliseconds since January mid-1970. That's how it represents longs internally. Then you have to think about, okay, when it actually arrives at Flink, that's called ingestion time. That's when Flink, the first processor that, Flink has for your data actually sees your event, and that's called ingestion time. And the third one is the window processing time. That's when the machines in your cluster are actually going to be processing that data. One of the things that you'll have to be aware of is that I think one of the first things you want to ask yourself is my data going to be time-stamped or not? Because if it has huge ramifications. If it's time-stamped, you can do much more with regards to processing out of order, late events, and things of that nature. If it's not time-stamped, you're sort of at the mercy of network latency and the speed of your machines in your cluster. Because once that timestamp is lost, it's lost. So you have to use what's called processing time, which is essentially the wall clock time of the computers that are running your Flink program. I talked about windows. Again, we have this infinite data coming in. So what do? You break it down. You break it down into smaller chunks that you can actually do something on, to work on. That's what windows are for. That is their purpose. And it gives you several flavors of windows that I want you to know about. And these are pretty cool things. They're very, quite powerful actually. Windows, and there's two main categories of the windows. You can have the time-based windows, or you can have the data-based windows. So time-based, you have three categories. You have what's called a tumbling window, you have a sliding window, and you have a session window. And for database, these are all out of the box. The out-of-the-box data-based window is called account window, so you'd want to know how many times, you want to be notified basically when you've seen a certain number of events of a certain type. I'm going to go through these one by one and give you a pretty concrete example of what they look like. Let's talk about what a tumbling window is. These are the non-overlapping windows. I'm trying to give you a simple use case here that you might use a tumbling window for. Show me what URLs users are clicking on every 10 minutes. So you've got a website and people are clicking on the pages and your manager wants to know who's clicking on what, and we want to know within a certain time period what's happening and what's going on. So here we have, you have to remember that the data is going to probably be keyed, because in this case, if you think about it, a very natural selection for the key would be the user ID. each person, you want to know what each person's doing when they're using your website, so you basically get a better idea of your user behavior. And you want to specify, well, what interval am I interested in? It could be anything. It could be what's happening every 5 seconds, what's happening every minute, what's happening every hour. The bottom line, and the important thing to keep in mind, is that the windows they don't overlap. It's just you go from 0 to 10 minutes, say, and then from 11 to 20, and then from 21 to 30. And you would get results computed for each of those time intervals also by whatever key that is what you're interested in. So here's just an example, graphical example of what that would look like when you have 3 users and you've got 5 windows going on with a certain window size. A sliding window is just like a tumbling window, except you kind of keep moving it along, and you keep asking what's going on every time with an additional time interval. So you might say, show me what URLs users clicked on in 10 minutes, but I want to know about it every 5 minutes. So this is more useful in terms of identifying trending, what's going on. You can see that as time progresses that you see more and more users clicking on things or not clicking on things. You might see a change in behavior. But think of it as it's just a tumbling, sort of like a tumbling window that you can slide along. So in this case, you might have events that show up in more than one window because they're overlapping. And this might be, again, if you want to, your management wants to know about, I want to know what's happened in the last 2 hours, but I want to be informed every 15 minutes. That's a sliding window. Session window. You have a website and people have sessions, and you want to identify what people are doing in those sessions. So this uses time too, but it's much different than the other 2 windows. This is the way you do this is you identify a session by a gap of activity. So you might say, if I don't see anything for 30 minutes from for a particular user, that's going to be our definition of a session ending and a new session beginning. So you define a session windows by what's called a session gap. And that's going to be some time period that is going to be custom to your solution, to your application, that you use to say, okay, all of these events from this particular key or this user or this event source, these all happened in one session, and then they stopped and they came back in another session and they did something else. So again, you can see the usefulness of this in identifying user behavior patterns and trends and whatnot, and how people are accessing and using resources and generating events. The last one, again out of the box, is something called the count window. This is not based on time. This is based on a number of things has reached the value that you're interested in. So you might have teams building products, and or you might have a factory building things, and every time, let's say you're building tires, and every time 4 tires are built, you said, well, I've got 4 tires, I'm ready to now start my process of packaging up my 4 tires for the next process in my chain here. So something about the number of events is important and triggers a computation on your part. So here I just have 3 different teams, and they're producing widgets, and you want to know every time a team produces 3 widgets, maybe you want to package them up, or you want to create a report, or you want to do something. But this is this mechanism will give you that flexibility, so you can say, okay, when I see 3 things, I want to do something. Again, key-based. So you have to think in terms of keys, and you have to think in terms of time differently. This, again, this I can't emphasize enough as something that's very important. You're going to have to think about a lot. And I tried to show a very graphical example here of this is just reality. Things don't always go according to plan. Things can show up late or out of order. So here, all I wanted to show you very directly is that you have a source, and it generates 2 events, and for whatever reason between that source and your Flink program, something happens, and Flink doesn't see A happening and B happening. What it sees is B happening before A happening, and unless you have event time and event stamps on those events, you're going to be in trouble. You won't be able to detect that. The good news is, if you do have timestamps, you can do something about it. When you're building your streaming application, you're going to, again, these are the questions. I wanted to put these on a slide so they're right there in front of you, so it gets you thinking about how am I going to design this thing, and what are my acceptance criteria for a streaming application. Does it matter if things are out of order? Does it matter if things are late? What is important to me? Do I have to have low latency? Do I have to have correctness? Do I have to have both? It's going to be very hard to get both. There's going to be trade-offs no matter what you do. But these are things that you have to keep in mind. How does Flink let you deal with this stuff? This is where it's got some really nice features, in my opinion. It has something called watermarks. It has a feature called side output late data, and it has something called allowed lateness, and I'm going to go over each one of those. What is a watermark? Remember, now, again, all of these, the baseline assumption that we're dealing with here is that your events have been timestamped at the source. If they're not timestamped, none of this doesn't work. You have to have something that says, here's the source of truth from when this event happened. So a watermark, remember, if your events are timestamped, then, and the user asks you for a window, like a tumbling window, then you have to sort of know, you have to figure out, well, when does my window start and when does my window end? Because I need to know when my window ends, because I need to do a computation when that happens. And that's what watermarks help you do. They kind of keep track of where you are in these events, in the event time space, if that makes sense, so that you can sort of detect when you've seen all of the events that make up a certain window, and you can do a computation. And I'm going to get to that in the next slide. But here's, for now, think of them as just, they're invisible timestamps. They're not really part of your, they're not an event that actually gets sent to you. It's something you're computing in your Flink program. And you can also think of them as an assertion. So a watermark of time t says, I've seen everything up until that time, and if something comes, if I see an event after that time that is less than me, but it comes after I've already declared that this watermark has been reached, I'm going to throw it out. So that's what you see on the right-hand side there. We have events T0 and T2, and we had T1. Now T1, in theory, should have been included. But since it arrived late, it arrived after the watermark sort of declared itself and said, I've seen everything up until time 2. T1, you're out of luck. I'm going to throw you away. Unless you do some things, and you can get around that if you want. It doesn't let you deal with that situation. Again, why do watermarks matter? It helps you with the situation we just saw. Watermarks aren't, they're not cast in stone. You can manipulate them. That's the good news. You can say, yeah, I've seen my watermark is currently at this value, but I'm going to give myself some wiggle room. So you can actually manipulate your watermarks and say, it's not, even though we think we're up at time 2, I'm going to pretend we're maybe 5 seconds earlier. Why would you do that? Because watermarks are used to trigger the computations when the window ends. And if you push the watermark back, even though you're reading timestamps of incoming events, and you can sort of push the clock back using a watermark, that lets you keep the window open so that more events keep coming in, and you get to process them. Of course, that comes with a cost and a benefit. The benefit is your results are going to be more accurate because things that wouldn't have made it into that window now will make it into that window because you're manipulating the watermark a little bit. You're allowing for delay period. You're allowing for a certain amount of lateness. But while that's happening, you have to wait. Your program has to wait until those late events arrive, which means you're not going to produce your output as rapidly as you want it to, or you're not going to get the latency. So your boss says, how come the program's not as fast as you want? Well, we have to wait for late things to arrive. That's the answer. Watermarks are a very complex topic, and I think it took me quite a while to understand them, and I think there's a very good article I'm going to refer you to read. It helped me tremendously in understanding watermarks, and I think if you're going to be doing streaming programming, you've got to get your head wrapped around watermarks, and it's not easy, and it's just going to take some hard work, but I'm trying to make it easier for you. So I've done some of the heavy lifting here and learned the hard way, oh wow, I got to really understand this stuff. The hard part is when you run a streaming program and you're looking at your windows, it's really hard to figure out if they're correct or not. You know, you see all this stuff come in and Flink says, okay, here's your windows. Well, how do I know my windows got generated properly? How do I know that the late events got included or not included based on the rules I've set up with my watermarks? And here's one thing that helps a lot to visualize this stuff. You don't think of time in one dimension, you think of time in two dimensions. That's a huge help with this. This fellow, Tyler Akaido from Google, has written some articles on this, which you're going to see in a second. And I got this from him, and he uses the two-dimensional time visualization technique to help watermarks become much more easy to visualize. So on the x-axis, we're going to put our event time. So the x-axis is when did things actually happen, and the y-axis, the processing time. Think of that as when did Flink see it. Okay, those are two separate things. You've got to keep them straight in your head. When did it happen? When do I see it? Here's a link to that streaming article. There's actually there's two parts to it. I've read this about 5 times. I'm going to read it probably another 5 times, but it's actually linked to directly from the Flink documentation. They say basically, go read this. If you understand what we're talking about with Flink watermarks and event time, read this. So I did, and it's not easy, but it's not lightning, but it does. If you take the time to read it, you will understand this much better. It'll help you tremendously. Okay. That's watermarks. And there's sorry? Okay, I've got 10 minutes left, so I'm going to try to wrap this up. So what else can you do with Flink streaming and processing lateness? It also has something called side output late data. And so again, Flink is trying to give you all these different strategies for dealing with a stream and what can go wrong and what kind of things can you do to deal with it. If you have late events, you can use a watermark and wait around for things to process. That's one approach. You can also say, look, we don't have the luxury of waiting around. We've got to produce output no matter what. But we are interested in knowing what the late events are. So Flink gives you something called side output late data. So what it'll do is your incoming stream will be processed just like it normally is, and you'll get your output stream just like you do on the right-hand side there. But it'll also it lets you designate a second stream that says, if anything's late, stick it here. So you get both sets of events. You get the events that arrived on time, and you get the events that did not arrive on time, and now it's up to you to decide, what do you want to do with this? What are you going to do with your late events? At least it identifies them for you. Now it's up to you to decide how to process them. But you have the flexibility to do it. Allowed lateness is the third major approach or feature that Flink provides to help you with this kind of problem. This is slightly different than the other two. What this one does is it says, I'm going to have my windows. Let's say I want to know all the events that happened within a certain time frame, like 10 minutes. And things might be late. That's okay. When my window is ready to be computed, go ahead and compute my window with whatever's in it at the time. But I'm also going to specify a delay allowed lateness value. Maybe it's 5 seconds, 10 seconds, something of that nature. And the rule is, if anything late arrives within that allowable lateness period, go back and add that event to the window and then recompute the window. So in this case, you're going to get your windows being computed multiple times potentially, depending on how you set things up. So is this something you want? Again, it's a use case maybe, depending on your business rules and what you're trying to do. So again, it's a feature that gives you the flexibility to deal with various scenarios. What you have to think about very carefully with this one is, should I compute stuff more than once? And if I compute things more than once, did I compute something as a result? Did I compute downstream data? Once I got my windows, I wrote them out to a sink and I said, here's the truth. And then you're kind of coming back later saying, oh, I'm sorry, that's not the truth. Something arrived late. Here's the truth. So it's like a kid on a school bus who arrives. The school bus leaves without the kid shows up. They send the bus back to pick up the kid, and they go back to the school a second time or a third time if there's another late kid. So maybe that's going to suit what your needs, but you have to again give it a great deal of thought, because if you've computed some pretty heavy-duty downstream data structures, what happens to them? Do you modify them? Do you delete them? Do you update them? What are you going to do? But at least you have the capability. You have that luxury now of being able to ask that question with this feature. Flink SQL. A lot of people want to do SQL in the big data world, so Flink gives you that opportunity just like Spark does. Two basic APIs. Here's the table API, like I mentioned, and there's a straight SQL API. And again, I'm going to give you a very concrete example, very simple stuff. Semantically, they're equivalent. It really comes down to, I don't know, I think it's really a matter of preference. You can do it either way. Concrete example for SQL, very simple. You get a CSV file that's got some transaction data in it. We've got a date, a posted date, a card number, description, a category, and an amount. And you're going to want to run some queries on this stuff. This is what's coming in that you want to process. Okay, how would you do it? Pretty simple with the table API. There it is. There's a sample piece of Java code that would do the query. I want to get the card number, the category, and the debit amount, and I want to sum that up. That's what the debit.sum syntax is. And I want to group by, maybe you've got multiple card numbers in your account, and you want to group by category. So this will say, per card, per category, here's basically where here's the sum of your expenses for that. That's the Java API. Bottom is, as I mentioned, the straight SQL code string that you would just write, like you'd write in a SQL query window. So again, you can use either approach. They both work fine. Here's another thing that's true. But here's the kicker. Flink lets you can take the SQL, and you don't just have to run it on a file. You could actually run it on a stream. So, you're kind of at the highest level of the abstraction layer here. So here's what it would look like. A stream comes in, you read it, it gets transformed into what's called a dynamic table. That's just an internal representation of your stream in sort of a format that SQL can go against. Then you've got a query going that actually says select star from, and then this can work, this can actually reference, guess what? Windows, like a tumbling window. So you get the result of that query, it goes back to a dynamic table, it goes back to a stream, so you can convert back and forth between streams and something that you can do queries on and write it back out to a stream pretty easily. This example is right here. This is right out of the Flink documentation. They showed this as an example. I actually sat down and I wrote a Java program that does this because I wanted to see it. And it works. It's pretty cool, actually. So we have a stream coming in. What is this doing? It's saying, it's your users of your website. It's an event log basically saying, here's what the users are clicking on in your website. So you've got a name, and you've got what time, and you've got what URL did they click on. So, Mary clicked on the product page, and then Bob clicked on the product page, and Liz clicked on the home page. And that's your stream coming in. Here's your select statement. That's running against a stream, not a table, okay, or a file. And then you're producing the output. And that can go to, either a file. You can just keep appending the results to the end of a file, or you can put those into a real database if you wanted to. But it's very powerful, and I believe this is how Uber does a lot of their processing for matching up drivers and cars and passengers. So that's something to take a good look at as well. Last thing I want to talk about is the Flink fault tolerance. When you, again, this is with respect to streaming. When you're streaming data, you have to think about and ask yourself, when I'm doing a computation on that stream, am I generating state or not? What is state? Well, state is, let's think about first what it means to not have state. If you're just transforming something, like one element comes in and you just output another element that's a slight change. There's something transformed about that element, but you only looked at one element. You looked at element A and you produced element B as output. That's stateless. There's nothing being computed that you have to keep around to remember. But what happens if you want to compute something over multiple elements? Let's say you had a stream of integers coming in. Just an endless supply of integers coming in on your stream, and your job is to compute the sum of those integers. Well, the sum is going to be a computation across not one element, but theoretically, an unlimited number of elements. So that's what I mean by state. You're computing something that spans many, many elements in your stream. Why is that important? We're going to see in a second. Here's again, simple example of stateful streaming. We got numbers coming in. We've got 5, and so the way to look at this is to read from left to right. So 5 comes in your source stream, 5 goes out, and we're computing the sum. So we start at 0. So we see 5. We start at 0. 5 comes in. What's our sum? Our sum is 5. 8 comes in. Our sum is 13. 2 comes in. Our sum is 15. And we keep track of that. That number 15, that's your state. That's what you've computed over those 3 elements. Why is state so important? Because your program can crash, and what happens to your state if it does. So you've got, again, you've got in your normal, at the top of the screen here, we've got our normal, happy path. Source stream comes in, you do your thing, you produce an output, you keep your states. And let's say something bad happens, somebody sends in some bad data, and you've got a bug in your code, and you didn't check to see if it's an integer, and you try to parse something and it doesn't parse correctly, and your app throws an exception, your app crashes. Now what happens to your state? Well, if you don't keep it around, it's gone. It's gone forever, and then your boss comes in and says, I want to, we need to keep track of everything that is coming on our stream for the last month, and you'd have to say, well, we don't have that anymore because our program crashed. So obviously that's a very bad situation. You don't want that. What we want to do is, if our program does crash, we want to restore that state and start up again with the state that we had, and then keep going and pick up from where we left off, and then keep generating new states. So in case your program has a bad crash or something like that, you can restore and keep going. You're going to see these terms a lot. You're going to see what's called exactly once semantic processing. When it comes to state, what does it mean? It just means that you don't miss something, you don't process it more than once, you process it exactly once with respect, and this is critical, with respect to affecting the state. It doesn't mean that you won't necessarily look at the same record more than once, but you'll only process it once in terms of how it affects the state that you're computing. That's what exactly one means. Semantic, it's a semantic term for really, how does it affect my state? Not whether I, read it a couple times because maybe your program's coming up several times. It's you process it once, your state changes because you've seen it, and then you're done with it. So Flink gives you that guarantee that you can do that. Obviously, you can't let your state just go away if your program crashes, so you have a way to back it up to something. You can back it, by default, it goes in memory, which is fine for testing. Obviously, you'd never do this in production. You would write it out to, the two common ways to keep your state around is you can write it out to the file system, like Hadoop HDFS, or it has something called RocksDB, which is a persistent key value store that integrates with Flink that will keep your state for you also, so that you can restore it if you have to restart your program. How do you restart your program? It gives you a couple ways. It'll do this automatically. I've actually run my programs. I've deliberately caused the problems to see it work. It's pretty cool. So you can say, you can specify 2 things about Flink with respect to state. where I want to keep it, where I want to back it up, which I just showed you. The second one is, well, what are my rules for how to restart? So it gives you three choices here. You can say, I don't want to do a restart, or you can say, okay, try to restart the app, maybe 3 times after waiting a minute, something like that. So it'll automatically try to start your program 3 times, and it'll wait a minute. If it crashes again, it'll wait 1 minute, it'll try it again, wait 1 minute, try it again, and if all of that gets exhausted, then your program ends, it crashes or stops. If you back up your state, you're okay because you can still restart it from that checkpoint. You can also say, keep restarting my program, but if the failure rate, if I see more than 5 failures per hour, something is seriously wrong, crash the program, stop it, we'll restore from state later. So, but if it doesn't, then keep trying to restart and keep going. So those are your choices for how to restart your program if you have these kinds of problems. So that's Flink checkpointing and stateful programming, stateful stream programming. So here's my summary of Flink for you. It's an excellent alternative to Spark. It gives you the high throughput and the low latency. It's got good memory management. Didn't go into a whole lot of detail on that, but that's what gives it its speed, like Spark. It's in memory. It has the built-in cyclic processing, so you don't have to write less code. It handles running cyclic programs, algorithms for you. It does batch processing like we saw. It does a great job with the stream processing. It does SQL. It does SQL with streaming. And it gives you the stateful streaming and the fault tolerance. And I believe that is my discussion, folks. So there you go. I hope this has been helpful. And it gives you some things to think about now, and at least you have a pretty good idea of what Flink can do for you. Do we have any questions that I can try to help out with?
I got one. One of the things about Spark is that I noticed when you went to the word count that you were actually implementing a splitter. And I've noticed that in the Spark API there's actually a split method. So I was wondering, was it, do you believe that the Flink API is behind the Spark API, or was that just an example where you wanted to focus on splitting the line and bringing in the input for that?
That was just an example of me showing how to split the line up. The bottom line is that it gives you a lot of built-in interfaces like the mapping function, the flat map function, and which I did not cover, but is also important, is that I showed you one way to implement that function. You've got 3 choices, really. You can do a sort of anonymous class right there in the middle of the code where you just build the splitter class. Right. I didn't do it that way because I think it's less readable. Right. You can also use Java lambdas, which again, I believe those are just less readable. Some people prefer them. That's really sort of a personal choice. Or you can break it out into a separate class and implement the interface, which is what I did. The reason I like that is because it's separate and because it shows you exactly what the types are of the parameters coming in, the things going out. So you don't have to think, you don't have to guess what was I processing. Okay, it's right there. So that's how I handled that.
No, that's valid because you just simply said how I handle that Spark is through a lambda function. And so, yeah, what you did is just enhance the readability of what you were trying to do.
Exactly. Yeah. So, but yeah, you can use lambdas. They'll work fine too.
Mm-hmm. I have a question here. By the way, before that, it's an excellent presentation. Got most out of Flink in 1 hour than I could read and thrown through the internet. Thank you. So, given that Flink is built ground up on a stream-based model, what if we have 2 different APIs, a data stream API and data set API, if it is meant to be operating on a stream-based model?
Yeah, I'm pretty sure they're going to merge those. So I think that's just a temporary situation. I agree that I think it shouldn't be too much work to sort of combine them into one unified API. But for now, yeah, that's just the way they've set the APIs up right now. So you have to use data set right now for files and data stream for the streaming API. They're very, very similar. You know, it's almost like you don't even notice them a whole heck of a lot. And we'll have to wait and see. I mean, Flink changes so frequently. It's when I started this talk, when I was studying Flink and starting to, you know, put something together for a presentation, I was using 1.4, and then it changed to 1.5 on me, and now it's up to 1.6 as we're going. So it's still changing very rapidly, and you might see that coming very soon. And I'm almost positive I saw in their documentation that they plan to merge those.
Okay.
So.
But I also see that you have a 5-day class in this. That this you can literally provide a class for this.
Yes.
Okay.
We can go. What I try to do here is give you the 50,000-foot view, so hopefully you can, after this, you can say, oh, at least I've got a pretty good idea what Flink is now and what it can do. This is more about the what. Mm-hmm. If you want to learn the how, we are offering that course, and we go into much more detail of how to put together a Flink program, how to actually write the code that handles watermarks and lateness and things of that nature, because it's for whatever reason, Flink just isn't, it just doesn't have that brand recognition that Spark has. It doesn't have as much sample code out there. It's harder to go to Stack Overflow and find a fully functioning Flink program. So I've done a lot of that on my own because I wanted to actually, you know, it's some pretty great stuff. I wanted to see it actually work. So I've, you know, like I showed you with the SQL streaming example, you know, that's right there, but I couldn't find the code to do it. So I wrote it, and that's in our course. All that kind of stuff. So if you want to learn more, we're trying to put together a course where we not just show you the what, but we show you the how to actually build an application. So you can go back and be productive on day one after you've taken that course and start writing Flink programs. Right?
Chris, what's the title of the course, and do you have any dates?
We don't at the moment.
Actually, I think SLI is going to offer it sometime in November or December. That's why I asked about the course, because I think it's on the SLI schedule. I can't remember, but I know it's either November or December.
Yeah, I forgot the exact name, but it is Java-based, so the name is essentially running Flink applications in Java. So I don't use Scala. I'm a Java developer. I put together all the examples in Java. So it's basically how to write Flink programs using Java 8. That's what we're going to teach.
Great. I know it's on the SLI schedule. I just can't remember where.
I think I did it too.
Right. So we're hoping that folks are interested in learning more, and we can teach you that course and show you really how to put together a Flink program.
Well, if there's any consolation, I work with Zeppelin, and I've noticed that Zeppelin has a Flink interpreter, so you know that's kind of nice. But anyway.
All right.
Good.
Well, thank you everybody for attending. I think I've got your emails. I'm not sure we can get you mine. I'd be glad to answer questions or.
Oh, don't worry. We'll put that out.
We'll make sure that the slides are available to you and that you can ask. You know, because my goal here is I want you to understand how to use. You know, I want to help you learn how to be productive using Flink. So if something isn't clear that I can help out, I'd be glad to.
The dates too.
Yeah, great. Oh, and we got the emails. We can follow that up
Right.
for those people who have it. Okay.
Well, thank you very much for attending, people, and I hope this has been helpful to you.
Thank you.
Thank you, Chris.
All right.